Hello and welcome back to the Cracking FAANG YouTube channel. Today we're solving Leetcode problem 996, number of squareful arrays. You guys know the drill. Before we get into it, please leave a like and a comment. It really helps me out the YouTube algorithm, and subscribe to the channel if you haven't already. Alright, an array is squareful if the sum of every pair of adjacent elements is a perfect square. Given an integer array nums, return the number of permutations of nums that are squareful. Two permutations, permutation 1 and permutation 2, are said to be different if there is some index I such that permutation 1 of I does not equal permutation 2 of I. So now that we read the question prompt, let's look at a very basic example and see how we would do this. So we were given the nums 1, 7, 18. So let's see, is this a valid permutation? So let's check these two pairwise elements. So this obviously sums up to 18. Which is not a perfect square. So that means that this permutation won't work. So we need to move these around a bit. So let's say we swap the 17 and the 8, right? So we'll swap the 1 with the 17. And obviously they can't be together again because we just saw that 1 and 17 don't make a perfect square. So let's swap these and then swap the 1 with the 8. So we'll do 17, 8, and 1. So let's check this now. So this adds up to 25, which we know is a perfect square because it's 5 squared. And this adds up to 9, which is also a perfect square because it's 3 squared, right? So this is a valid solution. So we have one valid solution. Okay, well, what's the other way we can arrange this? We know that 17 and 1 can't be next to each other. So that means that we have to basically switch the 17 and the 8 now. Let's see if that would work, right? So we could try maybe 8, 17 and 1, but again we have 17 and 1 together, so that doesn't work. So the only last thing we can do is actually just to swap the 8 and the 17 and see if that would work. So we have 1, 8, and 17, and again we see that this sums up to 9, this sums up to 25, so we are good to go, and that is our second permutation there, right? So our final solution would be to return 2 because there's only 2 permutations we can form. Relatively simple when you have a small amount of numbers here, but actually generating the solution for this is a little bit more complicated, but this is actually a medium problem in disguise because it's really not that hard. And what we're going to do now is we're just going to wipe away all of this kind of example, and we're just going to go through the basic intuition because even though this is a hard problem, like I said, it's actually a medium, and you can solve it with basically the same algorithm with just a small tweak. So let us now delete this, and we'll talk about what the algorithm here should be. The way that we want to solve this is actually going to be the same algorithm as Permutations II. And the reason that it's Permutations II is because there can actually be duplicates in this numbers here. So essentially what we need to do is just generate all of the permutations and check whether or not they actually fulfill our criteria, which remember, they just need to be perfect squares. So as we're going over our elements and kind of generating all the possibilities with a backtracking algorithm, we're just going to double check that we have perfect squares. If we do, great, we can add that current number, because remember, the current number plus whatever the previous number in our solution, when they add together, they need to be perfect squares. So what we're going to do is we're going to generate numbers, and what we need to do is, generally when we do backtracking, we're just going from left to right. But here, it could be the case that we skip over a number in the beginning, but then we need to come back to it later. So instead of strictly going from left to right, we're actually just going to iterate over the entire thing at each iteration of our loop here, because we basically need to access elements that we've used before, right? And we just want to make sure that like our current element that we're processing is not the same as the one before. Because let's say we just tried the number 2, because there can be duplicates. If the next number in our iteration here is also 2, then there's no point in checking it. So we can actually just continue through the loop here. And we also need to make sure that we actually have the perfect square. So essentially what we're going to do is, like I said, we're going to do a backtracking algorithm, backtrack. To basically build all the permutations, so all permutations here. We're going to build all of them and just check that the perfect square is enforced, and if it is, we can move forward. Otherwise, we might need to check that number later on to see if it would work. And then when we get to the end, we are basically done. So what we're going to do now is actually just go into the code editor. Again, we're just going to generate all the permutations. This is actually quite a complex solution. It's going to be n factorial. but that's fine because that's an accepted solution. In the worst case, all of the numbers you would be given, all the possible permutations would create perfect squares, or I guess squareful arrays. So you would just need to generate them all anyway. So in the worst case, it's going to be n factorial because that's how many permutations you can have here. So, all right, now that that's being said, let's actually go to the code and I will show you that this question is actually quite simple. And like I said, basically the same code as Permutations II. So let's now go to the editor and type this up. All right, let's now type this up. The first thing that we need to do is actually we're going to define a helper function to tell us whether or not we have a perfect square. So we're going to say def is perfect square. And what we're going to do here is we're going to take in a number. And this is basically just going to return if we have a perfect square. So the way that we're going to do this is we're going to return power. So we're going to raise int of whatever square root of num to the second power is and check whether or not we get the number. And the reason we use int here is because when num is actually not a perfect square, obviously let's say it's like we have 17. So that's going to be greater than 16, which is 4 squared. So it should be somewhere between 4 and 5, right? So we'll get like 4.1 whatever, but when we take the integer, it'll actually the int value, it'll round it down, right? And then when we raise it to the second power, it'll be obviously 16 now because 4.1 raised to truncated down will be 4. We raise it to the second power 16, and we're not actually going to get our number back. So this is going to tell us whether or not we actually got the number. And obviously for perfect squares, doing the integer truncation won't do anything because when we take the square root, we'll get an integer anyway. So nothing happens there. So this is our way of actually checking whether it's a perfect square. Now let's define in the main function our result. So this is going to be a list where we're actually just going to store all the permutations. So what we're going to do is we're going to define our DFS function and we're going to pass into it the numbers that we want to work with, our current path, and that's about it, right? So what we're going to do here is we're actually going to be modifying nums to basically keep track of what numbers we already used and which numbers we can actually use going forward. So if nums is empty, that means that we don't have any more available numbers to use because obviously we've already used them, right? We can't double use a number. We can only use it once. So what we're going to do is, unless it's a duplicate, in which case we can use it later. But in the case that they're all unique, then we can only use that number once, right? We can't use a number more than once in our permutation. That's just not how it works. So we're actually going to be modifying nums. So we're going to say if not nums, then we can we know that we've actually found a result. So we can say res.append, and we need to basically make a copy of our current path and add it to our result, right? And at this point, we can just return. Otherwise, what we want to do is we now want to check all the numbers to see whether or not we can actually add them to our permutation. So we're going to say for I in range len nums. What we're going to do now is we're going to say if I is actually greater than 0 and nums of I actually equals to nums of I minus 1, this indicates that we actually have a duplicate. So we essentially don't want to process this number because obviously we already processed it in the previous iteration, so there's no point of doing it again. We can actually just continue here because we can't have duplicates, so we want to skip them. Now what we want to do is we want to check whether or not we can actually add this value to our solution. So we're going to say if path because we need to basically check whether or not the current element plus the last element in our result, sorry, it should be current path. If we have a current path, then we can perform the check. Obviously, if there's no item, then we can't do anything there. So we're going to say if the current path is there, what we're going to do is we are going to say, okay, if the current path and not self dot is perfect square. So if we don't have a perfect square, so obviously the current path minus 1, so the last element in our solution, or our current solution, plus whatever the current number is, if adding these two together is not a perfect square, then obviously we don't have a squareful array, so we can't proceed forward. So again, we can just continue. Otherwise, if neither of these if statements trip up, then we know that we can actually add the current number I to our solution here. So we're going to say current path dot append whatever nums of I is. And then essentially what we want to do is we want to cut down our search space. So we're actually going to call DFS again because it's a backtracking, so we need to call it again. And now nums, what it needs to be is we want to take nums, so everything up until I plus everything from nums of I plus 1, because now we can no longer use nums of I because we've now used it. So we're essentially just removing it from our available numbers. Now what we're going to do is we're going to pass in the current path, and after this DFS runs, then we can just say current path dot pop. That will pop the last element we just added, similar to how we do it for most backtracking solutions. And then all we need to do now is simply call our DFS. And the way that we're checking these numbers only works actually if the numbers are actually sorted, right? Because if they're sorted, then obviously nums of I, if it's a duplicate, will be next to nums of I minus 1. So we actually want to pass in sorted nums here instead of the regular nums to ensure that we can actually do the check. So this is the same way you do it in Permutations II. You need to pre-sort it to actually do that. So we're going to say sorted nums, and we are going to pass an empty list because we obviously haven't made any path yet. So what we need to do now is basically just return the length of our results. So that's essentially how many results we were able to find is going to be our final solution. So let me just run this, make sure I didn't make any stupid syntax mistakes. And okay, we look good to go. Let's submit it. And let's see. Okay, accepted. Perfect. So as I mentioned previously, in the worst case, obviously, you're going to have, for the time complexity, you need to generate n factorial permutations, because in the worst case, all of the numbers in nums, no matter how you arrange them, all the permutations will actually create squareful arrays, which means that you just need to generate every single possible permutation from nums, and doing that is going to be n factorial. So for the space complexity, obviously we have our result here. We're making copies of this cur path, which in the worst case is going to be the length of nums. So for the space, in the case the result, we would have n factorial basically results being stored in our res here, right? So that's all the possible arrays we could do. So it's going to be big O of n factorial as well on the space. So that's how you do this question. Like I said, it's not too complicated. This is basically the same algorithm as the, what's it called? Actually, I think we can reduce the space here, actually. So if we just say res, we'll just say self.res equals 0. And instead of actually appending to our result here, what we're going to do is we're just going to say self.res plus equals to 1. And I think now what we can do is just return self.res, and this should actually take us down to big O of n. Let me just double check that. Looks fine still. And yeah, okay, that's a good optimization there. Yeah, we don't actually need the we don't actually need to store them because we don't care. We just care about the number of them. So we would just append it to res. So yeah, we can actually bring the space complexity down to big O of n. And the reason big O of n, because, well, first of all, you need to basically make a copy of sorted nums, and also sorting it takes big O of n space. So yeah, that's how you solve this question. Like I said, very similar to Permutations II in the sense that you're basically generating all the permutations, except a little bit different because you can use an older one later on based on if it's not a perfect square at the current moment, you need to be able to access it later, because adding it later on might then generate a pairwise perfect square. So yeah, a little bit different, but basically the same thing. Anyway, I've probably been blabbing for too long, so I'm going to end the video here. If you enjoyed the video, then leave a like and a comment. Helps me out with the YouTube algorithm. If you want to see more content like this, then subscribe to the channel. Otherwise, thanks so much for watching, and I'll see you in the next one. Bye!